Okay, thank you. You can start. Thank you very much.
Can I start directly, or do you want to
Yeah.
introduce? No, okay. Okay, so thanks to everybody. So today we're gonna see the role of energy storage with renewable electricity generation. So it's the impact and the opportunities of energy storage systems versus the electrical grid in conditions where you have a high share of renewable electrical power generation. What are the opportunities? What are the challenges? And what are the problems that we need to face for this kind of energy transition? So it will be more focused on the industrial application, but we're going to see that there are also many other market challenges and technological related challenges. So we're going to start with an introduction that I think it's worth to be done. So the preliminary consideration that needs to be done are related to the fact that we are very much used in considering the increase of population and improvement of gross domestic product coming together with the increase of energy demand, primary global energy demand. And this is a problem because if you want to relate one-to-one the wealth of a country with the energy demand of this country, it will be a never-ending race. So if we want to target a decarbonized world in 2050, we need to work on other aspects that will be not presented in the following presentation, but needs to be kept in mind very clearly. The best way to address this challenge is to go for energy efficiency. So instead of asking for more energy with a decarbonized vector and then consider ways to manage this decarbonized vector, like through energy storage system, one of the very first things that we can do is work on energy efficiency. So doesn't mean that we need to work only on production and the management of production, but definitely we need to try to decrease all the non-idealities and all the losses that we have in the system, because if you see out of this COVID dip, we have been increasing the energy demand over the last decades. But now what is desired, what we need to target is a peaking in this global primary energy demand and then reaching a plateau. Because otherwise, as I said, we will just be continuously adding new energy to the system, but the baseline will remain a carbon emission system. So instead, this is a scenario coming from the International Energy Agency that has been recalled several times, but you see that there are a lot of losses in all the energy chain. So from production to the final end user, there are a lot of losses, power system losses, losses in end use, but definitely we also need to work on more energy efficient systems. So just to make an example, here you can see that there is a negative contribution coming from heat pumps. So heating buildings and heating environments, industrial facilities through standard gas systems is not efficient. Instead, using heat pumps is very much more efficient. Same can be done for motors. So if you have internal combustion engines, those are very low efficiency energy systems. Instead, moving for electrical motors could increase these kind of things. So this is just a snapshot to give you the idea that we do not need only to work on the upstream part, but definitely also on the downstream part of the energy supply chain. Instead, if we start our consideration related to the production. So how am I going to produce this energy demand? We are in a world that is very much thermal energy based, I would say. So you can see that very clearly today. The majority of the global primary energy is covered by oil, coal, natural gas, and even bioenergy. And instead, we have pretty much 20% of the energy that is electricity. So how can we reach a decarbonized target in 2050? One of the things is to move towards electrification. So the short message and the second challenge that I want to mention is electrify as much as possible. Of course, not all the sectors can be properly electrified. There are those so-called hard to abate sectors that will remain critical. Typically, those are industrial sectors that need high temperatures. So steel sector, concrete, glass, ceramics need to reach in their processes high temperature, thousands of degrees, and definitely it's not a good approach to heat up at this high level of temperatures through electricity. So definitely we need to work on other stuff like decarbonized fuels or something like that. And then of course there is a topic that is related to goods transportation and people. So planes and ships hardly will ever be electrified. So again, working on different kind of fuels could be decarbonized production of standard fuel or electrical fuels, even hydrogen, these kind of things, is something that will be definitely dedicated to those sectors. So we will try to electrify as much as possible, but still you see that this is again, I would say this is again from International Energy Agency. If you look back, this is from 2024, but if you look back to the same reports of the same entity in the previous years, the scenarios were even more aggressive. So here you see we are going to move from 20% of electrical share to 40% electrical share. It's a lot. It means that you are more than doubling the electricity production that you have today. But if you look back in previous reports, the scenarios were even more aggressive. It seems that now IEA is well, giving a more conservative and probably more realistic outlook. Then, if we just focus on the electrical part of the problem, so again, from this slide, we are going to focus just on the dark blue color, okay? We can do a lot of things to decarbonize this sector because now the technologies are ready, and you see that the outlook that is similar to other technological advisors and scenarios makers. There will be a dominant role led by the renewables. So you see that today still electricity is very much produced through coal, and again this is a global picture, so of course it's a very country specific breakdown that you can have, but if you consider global electricity production that includes well, from Far East to our countries, to Africa, to North and South America, you still see that there is almost 1/3 of electricity that is provided through coal-fired engines. So then there is gas. Again, country-dependent based nuclear power and hydroelectric power. Those are the main vectors for electricity production as for today. But there is a very fast deployment rate, very fast deployment rate of photovoltaics and wind farms. And those two technology in various different applications will play the main role in the next decades. So already today, pretty much all the new electricity power plants that are installed worldwide are either photovoltaic or wind farms. There is still some room for hydropower, huge plants in some countries, but definitely it is already observed that it is not convenient, economically speaking, to install new power plants for electricity production based on gas or based on other technologies. On a global picture, photovoltaics and wind will be the dominant technologies. So then wind will be onshore or offshore. Solar can be as standalone, photovoltaics, or combined with storage system, as we're gonna see in the next slides. But what is evident is that 25 years from now, we're gonna have an electrical system that is very much dependent on renewables, and this means that we're gonna have some complexities to be managed because those renewables, well, hydropower is a little more programmable than the others, but for sure, wind and solar are non-programmable energy power sources. So the point is that we need to find ways to manage the imbalances between time imbalances between production and consumption. And those unbalances come on a daily basis, of course. As for solar, you can easily understand this, but even on seasonal basis, because there are other of course, variations of the available resource that needs to be considered. And of course, these unbalances cause also critical issues on the stability of the electrical grid because it comes together with frequency drift and voltage drift. So it's not only a matter of having the same amount of energy that I ask for, but also it's a matter of having the grid to be stable. Okay, so this is another challenge that needs to be faced. So just to give you an idea, there are some countries that are already facing this kind of issues because, of course, the renewables are installed at a different pace in different countries. So this is an example that we're already having in California. If you go back in 2018, people started to refer to this graph that is just the net demand, so demand minus offer of energy versus time. So people refer to this graph as the duck curve. So what happens here, I hope that you can see my mouse. What happens here is that you have an excess production of electricity with respect to the demand. And instead here in the evening, you have an excess of demand versus production. So you have this kind of imbalances. And this causes fluctuation of the price of electricity on the wholesale market. So this duck curve is mainly caused by the fact that in California you have mainly solar, so photovoltaics. So of course at noon you have the peak production, and instead you don't have the peak demand. Typically you have two peaks in the day for the demand of electricity. One is in the early morning, and the second one is the highest typically in the evening. So instead, you have a strong mismatch between photovoltaics production and electricity demand. And the point is that in 2023, in California, they had not the dark curve anymore, but what they call the canyon curve. So what happens? The point is that over the years in California, for market opportunities, not definitely for decarbonization purposes, but for market opportunities, you have a very sunny country and the technology costs little. A lot of photovoltaic power plants were connected to the grid. So this Jack curve continued to deep down, transforming into a canyon curve. And you see that in a few years, you have hours in the day where the demand is fully covered by photovoltaics. So is this good or not? Well, it is good in the sense that you can demonstrate that you can fully provide at noon electricity through a green energy source. The point is that you have a bad effect on the pricing of the electricity. So the operators needs to make business out of the photovoltaic power plants. So what happens is that at noon, the price on the wholesale market, not for the final user, but on the wholesale market, electricity is a commodity. The price of electricity is zero or even could be negative in some cases. That means that the operators that own the photovoltaic power plant do not sell electricity on those hours. So this erodes your business plan and makes more investment less interesting for the operators. So it is not good if you want to go even further beyond. So if you want to install even more renewable power sources, because you have this sort of a parasitic effect on the pricing. So every problem comes together with an opportunity. Instead, you can see that here you have an imbalance that causes high prices. So here on late afternoon, you can see that the fact that you do not have the sun shining, and instead you have people coming home back from work and starting using their home electricity appliances, causes an imbalanced demand versus production that causes high electricity prices. So this created already a reality right now in California, an opportunity for what is called arbitrage. So you can time shift the photovoltaic electricity produced during the day at noon through batteries, energy storage system, and time shift this electricity the evening when you have a premium price for the electricity. And what is interesting to see is that this is already from April 2024. Now it is even more than that, but about 1 year ago, the battery storage systems, that means mainly lithium batteries, were the largest electricity producing technology in certain hours of the day. So when you don't have the sun shining and you have residual contribution from wind or from imports, or you see in California you don't have a lot of nuclear, you have a residual here baseload of nuclear and geothermal, but you see that this light green peak is coming from energy storage system. And this happened just in a couple of years. So the market perceived the opportunity that came out from the Duck Canyon curve and started to install energy storage system. Those are standalone energy storage system that just do what is called arbitrage, or you can even call it speculation. So you buy electricity pretty much at zero, because at noon the electricity is for free if you are an operator, and you resell it at very high, at convenient price in the evening. So this is already something that is market driven. So the operators perceive it an opportunity, and the technology that is now leading this kind of application is we're going to refer to it as lithium ion energy storage system. But there are ways to manage these critical imbalances. As I said, California is quite extreme. Other countries have a more let's say, articulated energy mix, but it is very much representative of what could be an fully decarbonized electrical grid in the near future. So it can be done. Not necessarily entirely through these technologies, but this is something that can be managed. I said not entirely with this approach because these flexibility options that needs to be considered to make the electrical grid stable, even in this scenario of high shares of renewables, are partially coming from the energy storage system. But batteries, I would say, is just one option. You have many other way forward that needs to be put on the table and needs to be considered, and I'm gonna mention some of them briefly. So we're gonna see just a snapshot on these these three aspects. So electrical vehicles, curtailment, and demand response. So what are those options? So one is curtailment, or let's say proactive curtailment. So what is curtailment? Curtailment is an operation that the grid operator does versus the independent power producers. If the grid operator sees that there is an imbalance going on and you have a frequency drift and you have an excess of production coming from power plants, renewable power plants, there is an automatic message that comes from the grid operator to the independent power producer that limits the power that can be fed into the electrical grid. So even if you have a power plant that nominally can reach 100 megawatts, let's say, at a certain point of the day, you can receive a message that clamps, limits, clips, curtails your injection into the grid to 50 or even 0 megawatts. And this is at your own loss. So you have no premium for that. You are just losing money. And this is to keep the grid stable. So it's for safety issues that you can do that. But if you see a scenario that wants to promote a decarbonized electrical grid, you need to find a way that is in between. So if you just operate here at the very left of this graph, that means that the operators do not want to curtail themselves. To have a fully decarbonized electrical grid, you would need to invest a lot in energy storage system. So if you consider the cost for the system, and you can refer to the levelized cost of electricity. If you are not familiar with this metric, let's see that it is just a way to account for all the costs, investment costs and operative costs versus the quantity of electricity that can be produced over the entire lifetime of the system. So it considers everything. Let's say that if this number is high, it is bad in terms of cost of the electricity for all the involved stakeholders. So if you are on the extreme left of this plot, and it's the current scenario, I would say, if you want to decarbonize fully your system, you need to invest a lot in storage system. You need to put a lot of batteries in operations. Otherwise, there is no way that you can time shift wind production or solar production day to night or summer to winter, okay? But if you can find a way that is giving a premium and remuneration to the operators for a voluntary, proactive self-curtailment, you can try to transform what is intrinsically a non-programmable power plant into a firm power plant. So let's put it this way. If you have 100 megawatt photovoltaic power plant, but you accept to operate this plant at 50 megawatts, you have a more programmable power plant. You operate under a regime of voluntary self-curtailment, but you receive a premium for that, and you avoid the risk of hours in the day when the electricity has $0, €0 per kilowatt hour cost, and you will just be losing money in those cases. So it can be demonstrated that you have a minimum for the system. If you go for a full remuneration, that means that you are self-curtailing yourself at 90%. Of course, it doesn't make a lot of sense because you'll just be, wasting your capex investment. But this is referred as implicit storage. That means that you do not really need to put down all the gigawatt hours in terms of batteries into the system if you can properly exploit the fact that the technology for the production of electricity from solar and wind are quite cheap with respect to batteries, and that a balance of the cost versus benefits can be found this way. So it's called implicit storage. Another workaround methodology is to work on the demand side. So instead of having the time shifting of the production through batteries, that means I'm trying to match the production curve versus the demand curve. The demand response is an approach that tries to modify the demand profile curve. So again, in exchange for remuneration, if you give, let's say, bill advantages to industries and even final users, making them use the electricity mainly at noon if you are in a photovoltaic based electrical grid instead of using it in the evening or early in the morning, there is a natural matching that will be obtained by moving the demand curve towards the profile of production that you have in your system. Another way, again, is the fact that a lot of electrical vehicles are expected in our countries in the future. So the electrical vehicles are, of course, with batteries. So is there really a need to install so many stationary energy storage systems if in my country I have all these electrical vehicles? Let's say that 95% of the time my vehicle will be parked in the parking lot. So if we work on this vehicle to grid approach, there will be an operator between my electrical car and the grid operator. The operator is what is called an aggregator that will ask the permission to use the battery of my car while I'm not using my car. So I just need to communicate when I want my car to be available and with what level of state of charge of my battery at what time. But for the remaining time, if I have my car plugged into a bidirectional charging station, I will be able to give the energy storage system that is mounted on my chassis, on my car, to the system, and thousands and thousands of vehicles can easily replace the installation of stationary energy storage system. And again, this is a benefit for the entire system because in exchange for remuneration, I can let's say rent my battery mounted on my electrical vehicle to the aggregator, and this gives ancillary services and time shifting opportunities to the electrical system. It can be demonstrated that really the advantages can be huge. Of course, there is something that needs to be proven yet, that the electrical vehicles will really penetrate that much. Again, this is very much country-based. There are countries that are already with a high share of electrical vehicles, other are not, but this is something, again, depending on the country that you're operating, that needs to be considered, because this is a competitive technology in some ways, but also something that can very much be exploited in terms of market opportunity. So I gave you some different solutions to the same problem. The point is that this problem is quite young in age, because in the energy sector and in the electrical sector, there was no real need for storage. I mean, 1 ton of coal or 1 barrel of oil is already an energy storage system. So you just use it when you need it. And instead, electricity is not easily storable. Up to now, the most efficiency and biggest energy storage system has been the hydroelectric pumped system. So the pumped hydro is one of the main green energy storage technologies that we have, and one of the most efficient ones. But it wasn't so much in terms of storage needs. You had, as we have seen, a residual contribution of hydroelectric power in the electricity production in up to a few years ago. Now there is really a need for electricity storage, and that means that a lot of different technologies can play a role. Hydroelectric power can be done at a huge scale with high efficiency and even low cost per megawatt hour. The point is that pumped hydro is very, very site specific, so it has a huge impact on the environment. Definitely, you cannot place this technology everywhere. So these needs need to be obtained. These needs need to be solved through other kind of technologies. I mentioned it several times, the batteries, the electrochemical storage systems that are, as for today, one of the main technologies that we have and that we are using. Again, the point is that now you have two different applications of the storage system. You need to have stored electricity for power need and for energy need. The first one is more related to providing power services, so not for a long time, but high power on demand. And this can give you system stability and security, because those are typically the ancillary services that you offer to the grid to compensate for sudden drift of frequency, for instance. And the other topic is the energy needs. So you need to have uh, a longer duration of the storage system, because you need to cover many hours where you have these imbalances that I was referring to before between demand and production. Now, in this second part, we're going to see some of the technologies that are available today, or supposed to be available in the near future, to have these energy storage systems. And mainly then we're going to focus on the battery energy storage systems. So I already mentioned that hydroelectric pumped storage is the main and largest energy storage system that is installed at the global level today. I mean, I can spend some time on this, but it is, I think, quite familiar. It's just a sort of gravitational storage. You pump from the lower reservoir water up to the upper reservoir when you have an excess of electricity, and instead, when you have a lack of electricity, you just do the opposite through a generator, and this way the gravitational storage of the upper reservoir goes down to the lower reservoir, producing electricity. Other systems that are, again, mechanical systems are the compressed air energy storage system. You can exploit not necessarily vessels, but in some cases natural caves to do so. There are several variations of these technologies. Not all of them are mature. What is very, very much installed today is the battery energy storage system, so electrochemical storage, mainly lithium based, different technologies we're gonna see. In the near future, next future, depending on the cost that it's gonna have, you have, let's see, a molecular transformation of electricity. So if you want to transform electricity into molecules, you can split the water into hydrogen and oxygen through electrolyzers, and then you have hydrogen storage that can be reconverted into electricity through fuel cells. Um, Now the cost of this technology is very, very high, especially if you want to back convert hydrogen into electricity, because the round trip efficiency is quite low. But it is an alternative way that is very much pursued, also in terms of funding from the European community, for instance. Then you have other kind of storage that are kinetic, magnetic, and so on, and even thermal storage. But if we want to see the differences between all of these, again, you need to focus on two different axes. One is the typical duration that can be provided by these technologies, and the other is the scale at which those technologies can be applied. So if you just want to start from PHS, that is pumped hydro storage, the most mature storage system that you have for today, okay, it can have a duration that is from a few minutes or even half a minute up to weeks, because you have a reservoir that can be huge, and it can be applied at a very, very high scale, 1 gigawatt scale, for instance. But again, it cannot be placed everywhere, and it is very site specific. So you need to see also the other technologies. So hydrogen is not so mature, but again, as you translated everything into, let's say, a decarbonized fuel, it is like having a barrel of oil. You have a canister of hydrogen, so it could be even seasonal storage, okay? And potentially it can be applied at a huge scale, so from megawatts to gigawatt scale. But again, the main concern right now is more related to the cost of this technology. And same can be said for the compressed air energy storage system. Again, if you do not want to be involved into very high capex expenditures, you need to have natural places, natural caves where you can use these compression air systems, and it cannot be placed everywhere. Again, this site specificity tends to reduce a lot the real applicability of these technologies. Instead, what is very nice of these other systems, supercapacitors, flywheels, and batteries, is that all of these are devices, so very modular. You can place them pretty much everywhere with a decent footprint, but some limitations in terms of scale and duration. So supercapacitor typically can be a solution if you have a very power intensive need. So if you want to compensate for very fast frequency deviations, you can use supercapacitors, but this can be done typically for few seconds. Flywheels are in between, I would say, and batteries, depending on the electrochemistry that you have, can be a good solution, both in terms of large range for application, in terms of power, and in terms of duration. So here in the green box battery, there are many, many chemistries, different chemistries. What is the deployment status that we have as for today? So this is not a very recent pie chart, but in 2022, you can see that 3/4 of the storage systems were mainly based on pumped hydro systems, and 1/4 was lithium-ion batteries. And you see that the other technologies are very, very residual. So if you have the chance to see a more recent pie chart, you're gonna see that the pumped hydro is not increasing at all, I would say. So this level of gigawatt, 165 gigawatts, is very close to what we had 10 years ago and very close to what we are going to have 10 years from now. So what is really increasing in terms of installation is this electrochemistry, that is lithium ion batteries. And probably in the next years, you're going to see this yellow slice that is increasing a lot with respect to the remaining technologies. So as I said, there are different electrochemistries that are possible. Um, okay, lithium ion is the dominant technology. By the way, lithium ion doesn't mean a lot. You have different lithium ion electrochemistries. So it could be nickel, cobalt, aluminum, nickel, manganese, cobalt, or lithium iron phosphate. Uh, they come with different specificities, different energy densities, different costs, depending on the application. You prefer one versus the other. But let's say that generally speaking, lithium ion electrochemical storage systems are right now the leading technology for energy storage application, thanks to their interesting, I would say, not definitive cycle life. I mean, 6,000 cycles means that you can use the batteries for full discharge and recharging cycle up to 6,000 times without losing too much energy capacity. That means that typically the end of life of a battery is reached when you reach 80% of the original nominal capacity. So if you have 1 megawatt hour of storage on a new system, after 6,000 cycles, the manufacturer guarantees that you are still gonna have more than 0.8 megawatt hour, okay? So then, of course, the technology is evolving. I've seen recently cycles that are 8,000, 10,000, or even more in terms of warranties. Energy density is pretty high, not the highest for all the technologies, but pretty high. And especially for NMC technology that has the highest energy density is suitable for electrical vehicles with 800 kilometers range. And the duration is in the range of several hours, I would say. The lifespan, then we're going to refer to that, is the natural aging of the battery, can be 10 years. Recently, I've seen tenders where they offered lithium-ion batteries up to 20 years. That is a lot. Then, of course, we're going to see 20 years from now if this was real or not. And they have a very high round-trip efficiency. So you can have even 90% of round-trip efficiency. That means that if I'm charging my battery with 100 megawatt hour, I will be extracting from my battery 95 of these 100 megawatt hours. So I'm not losing that much in terms of side reactions or heating during the cycling process. And this is already at a large scale. So then you have other technologies, other electrochemistries with different specificities. You have vanadium flow batteries that can be interesting if you want to have high cycling of the systems. So typically, if you want to do just time shifting of a photovoltaic, you charge the battery at noon and you discharge it in the evening. That is pretty much one cycle per day. But if you want to cycle more the battery because you have power intensive applications, you are probably more interested in having other technologies that are not necessarily lithium based. So vanadium flow batteries, I don't have time to talk about this, but it is a completely different technologies that decouples fully the power from the capacity of the battery. And then you have some emerging technologies, less mature, iron based or zinc based. One that is already at high technological readiness level and is already commercial is the sodium sulfur battery. It was quite popular a few years ago, but now it appears to be less competitive than lithium. So sodium sulfur is not considered that much right now. It does not have differential features and specific value proposition aspects that can make it competitive with lithium ion. Instead, sodium ion is an emerging technology that is not mature yet, but could be very interesting in terms of improvements in the supply chain. As you can probably know already, lithium is, well, in terms of mining, is quite specific. You can extract lithium in a very few countries. The supply chain is quite critical, not because it is a rare material, but because it is a strategic material. It is critical. Instead, sodium ion batteries does not have lithium inside of them and are based on one of the most abundant materials that we have on Earth. So despite the fact that sodium ion probably will come at a higher cost with less performances in terms of reliability, in terms of cycle aging and so on, if the sodium ion batteries can provide a good enough energy density, probably for many applications they will be preferred with respect to lithium ion. It is not I mean, in the very short period, but you can see already announcements, even for the electrical vehicle sectors, that some of the big players are developing sodium ion batteries. So this is something that is emerging fast, and that could be very interesting to look at. So, stationary utility scale battery energy storage systems. You start from a cell, and here on the left you have what is called a prismatic cell that has this kind of shape. You put many of them in serial and parallel connections, and all these battery modules, so many cells, will be placed through racks into a cabinet and into containers to have these energy storage systems. So as you can see from this very naive picture, this is a very modular technology. Battery cells are manufactured on roll-to-roll machines that can go up to 50 or 60 meters per minute in terms of electrode deposition. So it is a very automatized process, and it can really reach volumes of scale and have the advantages of decreasing the cost. And in fact, over the last few years, this technology decreased a lot in terms of cost, and still the costs are not completely able to provide by themselves easy business cases. I would say you need to really find your spot in the market for that, but the decrease in the cost was amazing. In the last 10 years, it went down one order of magnitude. So these energy storage systems are not only the batteries, but for sure, in terms of overall cost, the cells play a major role. Okay. Then if you want to use them, you need to consider also the fact that you don't have only the batteries. The batteries, by the way, come together with what is called the BMS, so the battery management systems. That is the electronic board that controls the battery and that monitors the batteries to avoid any kind of overheating, over voltage, under voltage. So all the safety issues that can come on a bare battery. You cannot, let's say, communicate directly with the battery. The manufacturer will always provide you the battery together with the battery management system. So in a battery management system, you could have different providers. You do not necessarily have a single provider of the energy storage system overall. You can have one that it is giving you the battery plus BMS. Another player can give you the inverter, so the power conversion system that converts from DC, direct current, into AC, alternate current. And then you have all the connections and the transformers from low voltage to medium voltage, the auxiliary systems. You need to cool the container, you need to cool the cells to avoid thermal runaway and to avoid variations in the round trip efficiency of the system. I mean, it's not, let's say that the most complex part still remains at the battery cell level, but it is, well, a little system, okay? Still, it is a container. Now, each container can reach something like 40 feet container can be up to 5 megawatt hour, if I remember correctly. So you see that it's a decent footprint that is coming together with my storage needs. If I need 50 megawatt hour, it will just be 10 containers. It's not that much. And then you have some specific, well, this is quite boring slide, but it's a typical list of specifications that you need to keep in mind when you want to size, to design an energy storage system. So it is not only power and capacity, but many other aspects need to be considered. By the way, now one of the most interesting innovations in terms of technologies is the liquid-based cooling of the modules. So not air cooling anymore, but a much more efficient deionized water liquid cooling. Typically, it's a fluidodynamic circuit that is underneath the module, but in some cases, I have seen also batteries immersed into a liquid tank to keep them cold. Let's just move forward. The energy storage system naturally age. So you can, I mean, you can do as precise as possible. You can have the highest manufacturing quality that can be reached as for today. But even if I'm not using my battery at all, it ages like all of us. So this is what is called the calendar aging. It's an intrinsic degradation mechanism that is related to the unavoidable chemical reactions that you have between the electrodes and the electrolyte. But this natural calendar aging, and as I said, it could be something that is in between 10 and 20 years. If you still want to have something like 80% of the original energy capacity, this can be accelerated by this other phenomenon that is called the cycle aging. So the more I use my battery, the faster it will age. And this is also related to the fact that it depends on the kind of cycles that I'm doing. If I cycle my battery at high currents or very deep discharge profiles, it will age faster than if I just do small variation around the same state of charge at a low current. So again, this means that even if I have the exact same battery, the aging of that battery will depend on the application that I have. So if I have the same battery technology on a vehicle, it will age differently if with respect to an energy storage stationary system. Okay. And again, state of health, SOH, is what is typically considered to be the value that I said before, 80% of the original capacity. But I mean, this is also subject to some differences between the manufacturers. So it's not under a norm that you define the state of health, unfortunately. So I said that lithium ion is the dominant technology, but it is, as for the current needs that we have today in terms of applications, because this electrochemical system has a coupled performance in terms of power and energy. That means that if I want to have an energy storage system that is 1 megawatt, 1 megawatt hour, fine. And it means that I have a power control system, an inverter that is 1 megawatt, and a battery that has a capacity of 1 megawatt hour. And this means that if I discharge the battery at full power, it will last 1 hour, okay? If I want to target an application that has a longer duration, so let's say 10 hours, still I can do it through lithium-ion batteries, but it means that I keep the same power control system, the same inverter that I mentioned before, but I just need to add more and more batteries. So each battery will operate at a lower power, a lower current, but I need to add the capex, okay? Uh, it is not the case for all the technologies. I mentioned it quickly before, the fact that vanadium redox flow batteries can decouple the power from the capacity, the energy capacity. Lithium is not able to do so. So you can easily understand that at a certain point, you see 2 hours, 4 hours, 6 hours, you reach a plateau. So this is the installed capital cost per kilowatt hour. Okay. So if I start here and I move from 2 hours to 4 hours, I can have a decrease in the unity cost. But if I increase my system to guarantee for 8-10 hours, I'm reaching a plateau. It means that just if you want to have more hours, you just need to install more batteries and you're reaching a plateau. So you don't have decrease opportunities in that. And okay, this is a projection for the decrease of the cost in the next years. But the main point is that other technologies can have an intrinsic advantage in that. The battery is the main cost of an energy storage system, as I said. So lithium is used today up to 4 hours, will be used in the near future for 6-hour duration energy storage system, and there will be tenders this year and next year in Italy, for instance, that will mainly focus on lithium-ion storage system. But going beyond 8 hours, 10 hours, either you have a large decrease of the cost of the technology, and it doesn't seem that you have so much margin to do so, or other technologies can be competitive on these time horizons. So beyond 8 hours or 10 hours, I would say that technological competition is still very much open in terms of costs. Okay. And then, of course, you have other aspects that are related to criticality of the supply chain I mentioned before. But let's say that sodium ion could solve those critical issues, but not necessarily be able to provide at a competitive price very long durations. So do we really need ultra long duration systems? It depends. We're gonna see it later on. As for today, as I said, we have the lithium ion that is the dominant technology, just because up to now the electrical grids of the main countries that have a high share of renewables just needed to have 1, 2, maximum 4 hours duration. So it was a natural winner for lithium ion. Instead, if we want to see in the future what could be the market outlook and what could be the applications, we're gonna see in the next slides what can be the scenario. So, in terms of stationary energy storage systems, okay, there are the off-grid energy storage systems. This is just to give you an idea. If I'm in a full off-grid condition and I have loads, electrical loads to be feeded, I need to balance properly production and demand through energy storage system. But I'm not going to focus on these aspects. The off-grid systems are quite few in the world, especially at a large scale. Instead, what is very interesting in terms of market application is the opportunity that is coming from the utility scale and from the residential sector. So all these systems are grid connected and are developed for different purposes. The expectations for these markets are huge because you can see that there is a compound annual growth rate that is about 20% every year at a global level. So this is a very fast increasing market, and you can see that it is not very much region based. So Wood Mackenzie, here is the source, expects to have energy storage system installed in China, Europe, US, but pretty much all over the world, both for residential and for utility scale levels. This is a 10-year outlook, but you can see that if you consider 2024, the expectation are to double the installed storage systems in a very few years, in less than a decade. What is not mentioned here, but you need to work on the data, is the fact that, well, in 2023, 2024, the typical duration of the energy storage systems was 2 hours. So quite short, because you just needed it for little time shifting and mainly energy arbitrage, so frequency regulation or something like that. And on average, in 2030, so 5 years from now, it will be 3 hours. Again, it's an average. So if today we have 2 hours, it means that 5 years from now, we're going to install mainly 4 hours, and the average will be 3. But you see that there is this tendency to increase the duration of the energy storage system, and then I'm going to explain why. The main countries for the installations are by far United States and China, by far. Then you have Australia, mainly because the electrical grid in Australia is quite weak. So every time they install a non-programmable power source, could be solar or wind, but mainly solar, they need to try to make it as much programmable as they can. So in Australia, many photovoltaic power plants are authorized to be connected to the grid if they come together with energy storage systems already. And you see that it is evident by the fact that this azure color, the grid scale, is dominant in Australia. Instead, in Germany, you have a different situation. There are a lot of rooftop domestic residential installation of photovoltaics in Germany, and there you have this opportunity to install residential energy storage systems. Okay, this summarizes a little bit what I said. By the way, something that needs to be mentioned is the fact that in the United Kingdom, you don't have photovoltaics, you have wind farms. Many wind farms are bottom-mounted offshore wind farms, and the discontinuity in the production is creating troubles on the United Kingdom electrical grid. So that's why they are promoting a lot of tenders right now for the installation of grid-scale energy storage system, trying to avoid congestion and curtailment of the wind farms that they authorized already offshore. In India, you have the dark blue color mainly. I mean, you see that there's an interesting share for that. CCI means commercial and industrial. They are really trying to decarbonize themselves, but India is a very much coal-based country still, but there are opportunities there for that. And in Italy and Spain, you have balanced opportunities between grid scale and residential, I would say, in Japan as well. So the use cases are quite different. If I focus on the utility scale, I'm an operator. I'm a big guy. I can be also an independent power producer, but not necessarily, because I can use my energy storage system as a standalone system, and I can do what is called a trading or arbitrage or speculation, whatever. So I charge my battery at low price and I sell when the price of electricity is high. Or I can offer to the grid operator what is called an ancillary service, could be a service for frequency regulation that is paid as an annual fee, okay, from the grid operator. And then when the grid operator needs it, it can be with a maximum amount of hours per year. From remote, they operate my system. So then I can have the combination of my utility scale storage system together with a power production system, could be photovoltaics or wind. And this is a different market opportunity. I want to exploit at best the electricity that I'm producing from the renewable power sources. So if I'm in a country that is suffering a lot from curtailment or excess of photovoltaics production at noon, probably it is advantageous for me to try to postpone the injection into the grid of my peak power in late afternoon or even early morning of the day after by combining behind the meter, so before injecting into the grid, an energy storage system that is coupled with my photovoltaic or wind farm. Okay. And again, this can come together with other energy storage opportunities that are again the grid services, ancillary services that I can provide to the grid operator. But this is for the, let's say, the players on the electricity market. Instead, if I am a final user, I'm a company, I'm a manufacturer, and I have industrial electricity needs, I can install a battery together with my photovoltaic power plant that I have on the roof of my facility to optimize my self-consumption, so to optimize my bill, or if I have such a purpose, to decarbonize my production. So if I can demonstrate that I'm able to manufacture my goods with my own green energy that is time shifted on the production shifts that I have, it can come with an advantage on my final product. So this could be something that is considered at an industrial level, or same thing at a smaller scale on the residential level. I can have hardly a standalone battery at a residential level. I mean, it can be for backup, but really, it's not really a business case. Instead, especially in the European countries, but now it is coming pretty much everywhere, I can have my energy storage system integrated with the inverter that I have on that came with my rooftop photovoltaic system, and this is again for self-consumption, but it could be also to promote energy communities that will be with feed-in tariffs in the near future. Okay, as for utility scale, of course, you need to be you need to I mean, you need to decide where you want to play your game. It could be standalone, as I said, or integrated with other energy production units. I think that I already covered pretty much everything that is in this slide. Okay, so we can move forward. But as for the use cases of those utility scale battery energy storage system, the electrical markets are quite complex and not all of them can be compared one versus the other, but let's say that power intensive systems are the ones that you see on the left part of the slide. So frequency regulation mainly, in some cases also voltage regulation, and you can be asked to provide reactive power instead of active power. But typically, these kind of services are need to be very fast. So in that sense, you can understand that a technology like the electrochemical technology, for instance, lithium ion, is a very good player because it can respond in less than 1 second. Then for sure, this is not the case for hydropower or gas turbines. But on the other extreme, on the very right part of the slide, you can have hours, many hours. So this is for another kind of need. Of course, if you are off grid and you need to have island operation, you need to have all the hours that are needed. But even for other kind of dynamics compensation, so could be a profile of wind farms that are off for an entire day, or photovoltaics that is not producing overnight. You have needs that can be many hours. I'm not speaking about seasonal storage that is even on a monthly scale, but on the many hours, you will have more needs in the future. Up to now, the markets were very much focused on the left part of the applications. And this gives you an idea. This is the market for the utility scale battery energy storage system. And you see that, well, now in 2023, 2024, this purple color is decreasing. You see that all the opportunities in the last decades were related to those ancillary services that I referred to. So those are services that you provide to the grid operator to keep the grid, the electrical grid, stable. Instead, what is increasing right now are these two colors. One is this greenish color, the energy trading. Why? Because in some countries, as I said, there is a strong imbalance between production and demand that is already creating a spread in the intraday price of the electricity. So you can exploit it through an energy storage system. And capacity is the fact that you are, let's say, renting your energy storage system to the grid operator that in case of need, in case of emergency, can use the energy storage system that you are paid for to compensate for the imbalances of the grid. It could be either for charging the battery, and that means increasing the demand side, or discharging the battery, that means increasing the production side. But it seems that, especially in the markets in the countries where you already had many renewables and a certain level of energy storage installation, it seems that the opportunities for the ancillary markets are saturating. And in the near future, probably you're going to have more opportunities in terms of spread of prices of electricity. So that means arbitrage opportunities. And that means that for those applications, you need to have an energy intensive system. Okay. So the majority of the current installation have been between 1 hour and 4 hours, because the needs of the market were to solve the stability issues that were coming out. But once the grid is stabilized, you can have opportunities in time shifting. That means you want to have more hours. That means that you want to have more energy that can be moved from a low cost period to a high cost period in terms of electricity. Okay. So this is a more specific country-based scenario. That means that in European countries, you can have different energy storage opportunities. It's just to associate a single color per country. You have many tenders and auctions in those countries that are mainly driven by the grid operators that want to have a decarbonized grid that is stable. By the way, you know that the European electrical grid is interconnected, so all these decisions need to be taken at a European level, because if you have a problem in Iberia, you've seen that recently they had a blackout. This can have an impact in all the rest of the countries. If you have a frequency variation in Sicily, this frequency variation is observed in Ireland. Okay, So once you have, when you are losing a part of the grid, you need to decouple and interrupt the connection. But the frequency and the electrical grid is the same for all the continent. That's the point. So other here mentioned are other market opportunities, but it's more, let's say, business related, and I don't want to enter into this level of details. Instead, what is something that can be easily understood is that it is a general rule of thumb. If you increase the share of renewable electricity into your electrical grid, you will need to have storage systems that are of a higher duration. So again, it's a rule of thumb, but let's say that up to now we had a percentage of annual energy coming from renewables in the countries that was well below 40%, and that means that the energy storage needs from the system were well below 2 hours. Instead, if you have shares that increase a lot and you continue to install a lot of wind and then solar, at a certain point you will need to have longer duration. Again, this is related to the fact that you will be fully unbalancing demand and production, because if you install more renewables, you will phase out completely the gas turbines and the coal plants. So how can I obtain a base load? It could come from nuclear, but then you will need to manage also these daily imbalances that you have. So uh, when you have, let's say, over 60% of penetration of renewables, probably you're gonna face the issue of having something like 12 hours long duration energy storage systems. And this is critical because probably we don't have the technology yet to do so, okay? So of course it is not a problem that we have today, but as you are researchers, you need to see in the future. And the point is that at a certain point, we would need even seasonal storage systems. So it could be that those needs will be solved by a completely different approach. Could be, let's say, conversion of electricity into molecules, like I mentioned, hydrogen, to having this kind of seasonal storage, chemical storage systems. But this is something that we don't see an easy solution in the short period. Of course, those needs will emerge at a different time scale depending on the country. So you can see that now storage is well enough to provide the network balancing. But in some countries where you have high shares of renewables, at a certain point, you're gonna see that you see renewable supply when if refer to this one, okay, 60%, when I'm gonna reach 60% of renewables in the electricity production, 60% can come here in Spain already in 2025. Today, they are installing a lot of photovoltaics. Instead, in France, it will come, could be in 2040. They are not installing that much of renewables because they already have a decarbonized energy vector that is nuclear. So those are scenarios, but it means the short message is that it will depend very much on the country when we are going to need long duration energy storage systems. Okay, so 6 hours can be enough in up to now, but then you see you're going to have this kind of things. So this is the storage capacity that will be needed in the US, for example, market case, and those colors define the durations, okay? So you see that, okay, this is the pumped hydro storage, the historical way to do storage. But what is interesting, you see that NRL, National Renewable Energy Lab, in US, do not expect any kind of increase in this technology. So pumped hydro that you have in 2020 will remain the same in 2050. There is no more room to install more pumped hydro storage system. And of course, this is an intrinsic, very long duration energy storage system. And by the way, in Italy, we also have those already. But then you see this purple color that is coming out, so 2 hours battery storage. But since 2027, you are starting to have 4 hours duration battery energy storage system. So what is expected in the US is that in 2037, the duration required and all the market opportunities will promote 6 hours durations, 8 hours, etc. So again, it is not a very fast increase in the duration for sure, but you see that this regime from 8 to 12 hours is something that will come in the next decade, or well, after 2035. And definitely, I don't think that we have the technology as for today that is a competitive technology. And lithium ion has a critical supply chain, so no way that you can install something like 200 gigawatts with this technology in a single country. Okay. So short message, technological competition is open for long duration storage needs. Then if you have a look not only to the other electrochemistries that I mentioned before, but to complete different systems, you can see that again, those systems are trying to be competitive on a long duration. So those are the typical durations that you have for all those technologies. And lithium ion, definitely up to 6 hours, there is no competition. They will win. They will win for sure. Okay. But instead, for the other systems, you can have competition. And for instance, here you have a 10-hour duration. And here what is calculated is the capex cost, so dollars per kilowatt hour. So you can see already that there are technologies that can be on a 10 hours duration scale more competitive than lithium ion. Then the truth is that today you don't have those needs. Nobody needs 10-hour duration. There's no market that needs 10 hours duration. But it already means that 10 years from now, one of those guys, not lithium ion, will win the race. Okay. So I'm done with the technical part. I wanted to conclude with some of the experience that my company is doing on the energy storage system. So I just wanted to mention a couple of projects that we've been involved into. So the branch of Eni is an energy company that started from the oil and gas sector, and still it's the core business, the biggest oil and gas Italian company. But since 2020, there is a separated branch that is called Eni Plenitude that has the mission to install green electricity sources, so solar and wind. And of course, as I mentioned already, this will come together with energy storage systems. So the target is this one. So we want to increase the installation at a gigawatt per year pace. And we are already over 4 gigawatts of installed power plants. This is a not very recent slide, I have to say, but you see that depending on the country where we focus our business, it could be more wind in Italy or more solar in the US, but we are starting to have this orange part that is the storage systems. For the rest, the portfolio is pretty much split into 50-50 between solar and wind. But the storage is something that definitely is coming. So for instance, in Italy, we are operating a medium scale energy storage system for providing ancillary services, and this is for fast frequency reserve, so frequency regulation in short terms. And as you can see here, it's a very short duration system. It's about 40 minutes if you discharge the batteries at full power, it will last 40 minutes because it was for a power intensive application. And it was back 2023, if I remember correctly, that we have been this project authorized. This was our first energy storage systems. But just to give you an idea, now we have another opportunity. It is no more a frequency regulation, but instead it's real arbitrage. So trading of energy in Texas. In Texas, you have a lot of wind and a lot of sun, and you have a lot of power plants that are either photovoltaics or wind farms. That means that at midday, typically the cost of electricity is zero for the operators. The price, sorry, of the electricity is zero. That means that you have a large delta, a large spread of the electricity price intraday. That means that you have the possibility to operate a standalone energy storage system, charge and discharge, and make business out of it. So this is an independent energy storage system that is 200 megawatt and 200 megawatt hours. So it is quite huge. And you can see, I would say it's just two cases, but you can already perceive that in 2-3 years, we changed the business case, we changed the duration of the energy storage system, and we even changed the technology. So the first technology, well, this one, sorry, LFP, but definitely for energy storage system, lithium iron phosphate is better than other lithium technologies because of its lower cost per megawatt hour, despite the smaller energy density. Okay, and this will be finalized this year and will start operation at the end of this year. So those are just two examples, but definitely you need to monitor the technologies if you want to operate in this competitive market, because a lot of opportunities are coming in the near future. And that's it. Thank you very much. So if you have questions, I think that you could write them in the chat. So let me check. I'm interrupting the presentation right now to check if there are questions already. Okay, otherwise you can just raise your hand and ask for questions. Thank you.
Yes, I have any questions, let us know. But for now, I don't see any questions in the chat. So I think we can close the seminar. Thank you very much, Giacomo, for your presentation. So it will be put on the StoRIES YouTube channel, and we will be promoting it on all of our social media channels for those who did not manage to attend. You can also see it online, and we will also share it on the website as well as our newsletter. And yes, so we'll share the recording online as well. So with that, we can also close the meeting. Thank you very much for your presentation, and we'll share it with you very soon. Thank you very much.
Have a nice day.
Thank you. Bye-bye.